Okay. Many of you are probably wondering about this image here. It is a technique called a chronocyclograph. It was developed in the early 20th century as a way to analyze the motions and movements of the hands while working with machines. And so the thing that this work that we're looking at is we're interested in sort of these kind of bimanual behaviors of people working with sort of modern pen and multi-touch systems. Bimanual interaction actually has a long history in HCI. His is Ivan Sutherland's sketchpad from 1963. You can see he's using his left non-preferred hand to press buttons, which define the sort of operations and modify the operations performed with his right hand, preferred hand holding a light pen. Advanced some 50 years later, and we have these commercially available multi-pen and multi-touch devices that let you directly interact with your hands on the surface, such as this Wacom Cintiq display. And as a result, we've seen a number of new interaction techniques built around these new devices and these capabilities. Many of these techniques build upon Guillard's principles of bimanual asymmetry and how humans work with physical objects, and how there's a division of labor where the non-preferred hand will initiate and frame the actions of the preferred hand. As a result, we've had a number of new gestural interaction techniques that use a combination of edge-constrained gestures, such as the case of Ivan Sutherland's sketchpad, where you had him operating in the periphery with the buttons, to the more contextual ones, like the one presented here, where you have a two-finger gesture with the non-preferred left hand, creating a line, which then allows the user to perform different operations with their right hand. A lot of the work with these kinds of techniques has been focused on controlled tasks, looking at the usability of them and how much people enjoy them, and how efficient it makes them. But we're kind of wondering what happens when we take these techniques, combine them together into sort of a complete system, and look at sort of what happens in the real world activities. Because the thing is that as humans, we don't plan out an action and then perform. We don't plan out a task and then perform a set of actions. Those actions are situated in ad hoc. We improvise and adapt the system, adapt our approach based on the task. So we conducted a technology probe looking at the bimanual behaviors of users using a bimanual pen and touch system called Emma, which was part of what I developed during my dissertation. And we looked at this in landscape architecture design studio education. So Emma is a bimanual pen and touch system that lets users collect and compose visual imagery from the web or their local resources while allowing them to sketch over those images. And so here you're going to see just quickly a video here. This landscape architecture student has collecting images about a specific site, about bridges, and now he's sketching over them and there's a little edge-constrained region there where he does undo, manipulating the canvas. I'm not going to talk too much about Emma because that's not really what this paper is about. So we conducted, the technology probe happened in a graduate landscape architecture design studio called Professional Study. We had 3 participants, 3 master's students. They were all right-handed, and they were working on industry-sponsored projects. They were working on real sites where they needed to come up with real design solutions, but they were in the very early stages of the work, so they were not, at this point, they were collecting reference images and things about the site and doing a lot of sort of visual analysis in terms of coming up with a design. To collect data in the study, we used a combination of 2 cameras, one you see on the side and one overhead, so that we can avoid any potential occlusion issues of the hands, and then combine that with a capture of the screen of what they were doing. And we composited those all into one video, which we could then analyze. So we collected just over 10 hours of video, and we used a visual grounded theory approach. I'm not going to go too much into the approach. There's more details in the paper, but the idea here is that we are we're looking at the video and going through and transcribing and performing sort of a selective interpretation of what's going on. And what we did was we transcribed the actions that they were performing, as well as sort of the movements and positions of the hands. And then we began to code those hand positions and iterate on them to come up finally with a set of codes. So the main finding that we had was of a phenomenon that we identify as interstices. Interstices is a term that comes from architecture, which describes a space between spaces. And so the idea here is that interstices are periods between interaction that represent sustained spatial and kinesthetic relationships between hands and surfaces. And I'm going to go into more about what that exactly means. But the interesting thing about them is that they reveal aspects of engagement of the hands, and as well as anticipation towards future use. So the most interesting things that we saw with the interstices were mostly with the non-preferred hand, and we identified 3 of them: hovering, away, and rested. So a hovering interstice represents something that represents a very engaged hand that is held close to the surface with the fingers extended outward. What you'll see here in this example is right now she is performing a perspective transform on an image using her left non-preferred hand to specify a pivot point, while the right hand with the pen with pressure pushes and rotates the image in 3D space. And then what we'll see is that as she finishes, she pulls her left hand away, but it remains there, hovering near the surface, fingers still extended outward. She's doing some manipulations of the image to try and align it with the other one, and she realizes she needs to zoom in a bit more, continues to do some sort of fine-grained manipulations, and then now she's going to go back and do another perspective transform, finer grain one, to make it more closely match the one she already has. So the second interstice that we identified was away. Away represents a less sort of a certain uncertainty about the interaction, about what the hand is going to be needed or not. It's a bit like hovering in that the hand is left floating in air, but it is pulled back away from the surface. So here the participant is performing a opacity transformation by doing a 3-finger gesture on the edge-constrained region, and then using the pen to apply the transformation. And then we'll see once she finishes, she pulls her hand away. It's not resting on her lap, it's still holding in air. And in a second, we'll see her sort of hesitantly move the hand back towards the surface with the intent to interact. But still, it remains kind of pull back away, not really. The fingers are a little bit more turned down, away, not pointed directly at the surface. And then finally, we have the rested interstice. And rested, obviously, is the case where the hand is rested on the lap or on a non-interactive object. So here the participant is doing some drawing, and she has her left hand rested on her lap. And she'll make a mark, and can have that mark, wants to undo it, and then puts her hand back down on her lap. So here we have a breakdown of all the coded instances for the 3 participants. You can see that there's quite a bit of difference between their uses of the different interstices, and this is reflected partly in personal preference, but also a lot in their tasks. G1 primarily sketched over images, a very unimanual task where she doesn't have to do a lot of the bimanual asymmetric interactions, whereas G2 heavily used bimanual asymmetric interactions. She would actually hover her left hand near the edge-constrained gesture region near the bottom of the screen and perform a mix of swipes and touches on this area, this edge-constrained area, along with contextual gestures, sort of to create a way for her to really efficiently interact with the software in a very sort of expert way. And then finally, G3 rested her hand primarily most of the time. She was doing mostly a lot of very unimanual interactions with mostly her bimanual. Her use of the left hand tended to be for undoing things and so forth. So that was a study with 3 participants, and we identified the phenomenon, but we were wondering, well, that's 3 participants, maybe it's just unique to them or unique to their task. And so we conducted a second study to validate this finding involving 2 undergraduate landscape architecture studios with 14 participants. We used the same data collection method, but this time, in terms of the coding, we already knew what we were looking for, so we had a very phenomenon-specific coding, and we collected over almost 22 hours of video data. And so rather than code all of that, we selected to take 30-minute samples from each participant's video in the middle, so to avoid any of the sort of learning setup time or the ending shutdown time. And so here we can see the findings, the breakdowns of the codes for those 30-minute samples for the 14 participants. We see, again, hovering away and rested appeared with these participants, so we feel confident that it is a phenomenon that exists. As well, we identified a new interstice that we call stabilizing. So a stabilizing interstice is one where the non-preferred hand is used to stabilize the actions of the preferred hand. So in one of the tasks one of the design studios, the participants had to create journal entries where they would take photos around campus and analyze those photos and then write up descriptions. And so they were doing actually a lot of handwriting. And there was some, I think, hesitant to, because we had this in-house sensor for the touch input, and so there were some potential issues of them not wanting to interfere with that, and so they would use the hold. You can see here he's holding near his elbow with his left hand while his right hand can write. So looking at what makes an interstice, and so they have a spatial quality. They reflect a level of engagement where the hand is either, in the case of hovering, it's close. In the case of pull back, it's a little bit further away, and then rested, it's completely sort of disengaged from the surface. It's temporal, and that it is a sustained behavior. It's not something that they're just doing. The idea is not that it's any part of the movement. It is a sustained gesture. And also it has a kinesthetic component, in that the hands, the fingers themselves, as I was showing with hovering, the fingers are pointed towards the surface, ready to engage, whereas pulled back, the fingers curl inward a little bit more, and then rested, the fingers are sort of completely disengaged. And this, like I was saying, they represent these levels of engagement. So there have been existing surface interaction models that have described the level of engagement with touch input. This particular model, you approach, then you have a pre-input phase where your hand is moving towards the surface, and then you have the actual input performed, and then there's a post-input phase, and that loops back around, or you can leave. And the idea here is that a number of prior work have looked at designing gestural interaction around these pre- and post-input phases. And what we're arguing is that there's actually a missing phase here with the interstices, because they represent a sustained behavior that is not part of the gestures of pulling the hand away and towards the surface, but they actually represent, in this case, we can see the left hand, in the case of G2, holding her left hand near the surface while she was continuing to interact with her right hand. And so it is, there's not just this jump straight from post to pre-input, but a state in between. And each interstice has a different level of sort of engagement. So we had the case of the hovering hand would be much more engaged on this graph, whereas a rested interstice would be much lower. So the interesting thing that we think about interstices is they seem to represent, they are patterns that are interaction patterns that participants learn to do as they begin to use the system. And so they seem to represent an aspect of expert use. And that actually we're interested in seeing how maybe we could design sort of co-adaptive interfaces that as users initially the interface will provide sort of more feed-forward mechanisms to sort of teach the user how to interact, but then it should begin to learn and adapt to their interaction patterns, and seeing as they begin to perform specific kinds of gestures in specific areas to then provide more context-aware interfaces. As well, this has implications for a lot of above-surface gestural interaction. We feel like there's kind of this sense that maybe we're able to create these more expressive interactions by allowing people to express things in the air above the surface, as if this space was not being used by users before that, because it was not being sensed, right? And in fact, actually, we've shown that they do use this space to have specific behaviors that support their expert use of the system. So in concluding, we've identified this phenomenon of interstices, which represent the sustained spatial and kinesthetic relationships between hands and surfaces that reveal aspects of anticipation towards future use. They arose through their improvisation rather than these weren't designed interactions that we created or something that they planned out. They just arose through their actual use in real-world tasks. And we, of course, encourage further study looking beyond just what we've collected here is looking at other, obviously, input modalities, because we think this is present elsewhere, but also other ways to evaluate interstices and to get at more of the fine-grained details that we could not get just from analyzing video data. And then I want to just acknowledge that this work was supported by ERC grant, an NSF grant, and Wacom Technologies. And I will take questions.
So please, so if you have any questions, go to the microphone.
Hello, Fabrice Matulik, Preferred Networks. So this is an interesting study and exploration. I was wondering how valuable that information is, the interstices, compared to pre-input and post-input. Because they would assume that people just have their hand here waiting for whatever they need to do next, but it's not immediate, as you said, right? So I wonder how that can be used for your interface for the task at hand, compared to like pre-input, where you, let's say, there's another paper where the location of the thumb determines where the menu is going to appear. That seems to be like a very valuable information. So could you elaborate on?
Right. It's a good question. So I do think that there is a part of this that is it's intended to be. I think the idea here would be to, as I was saying, potentially to have contextual interfaces that, as I begin to, if I am hovering my hand at a specific time and doing a similar set of interactions, then I can potentially provide you with the user with an interface to perform those operations when your hand is in that doing that behavior. Right? It can support sort of contextual aware interfaces.
So that's when the hand is hovering, but when it's like under the table.
Right. When it's rested, it's kind of. I would argue that it's. Yes, it's informative in that it shows a lack of engagement of the hand, and it also shows that in those tasks they're probably doing mostly unimanual interactions. In this case, with Emma, it was with the pen, and that you could provide. In that case, you could provide contextual tools for sketching, which might change if their hand is hovering in the air. Right.
Thank you.
Any more questions? So I have one for you. I noticed that in your study you have the machine set up in this way. So is there any particular reason for that?
Because that reflects kind of the drafting table style that is common in architecture. And certainly I would say that the things that we observed are going to vary if you change to a vertical display or a tabletop display, that the same interstices and the same the amounts, obviously on a vertical display, they're probably going to hover less because it's more physically exhausting.
Right. Okay. So we do have time for more questions. So please. And maybe I ask another one. So did you notice any changes, like during the process, like maybe at the beginning they are not tired, so they have more hovering gestures, and after a while they are tired and they have more resting?
I did not observe any of that, and it would be interesting to go back and try and see if there was something there. I do think that I did find that actually, especially with the first participants, that and they performed. It took place over 3 sessions, and so that in the later sessions, I believe we began to see more of the hovering behavior as they became more familiar with the tool and how sort of this idea that they're adapting these and forming these expert behaviors.
That's good. Okay, so if we have no further questions, let's move to the next speaker.